All right, welcome back to the deep dive. Today we're diving into shape memory alloys, or SMAs. These are those materials that can, they can kind of remember their original shape even after you bend them or twist them. They're finding their way into more and more technologies, from automotive components and aerospace to even robotics and biomedical implants. Pretty wild stuff.
Yeah, it is. It is. And in this deep dive, we're going to be looking at a collection of scientific articles that really break down the science behind these materials.
Yeah.
And one thing that a lot of these studies highlight is this problem of, well, how SMAs can sometimes lose their ability to fully bounce back to their original shape, like they experience some sort of memory loss.
Interesting. So they don't always fully recover. What's the root cause of that?
Well, often it comes down to, it's something called slip at the atomic level. What happens is, layers of atoms within the material's crystal structure, they kind of slide past each other. And understanding this slip, how to prevent it or mitigate it, that's really crucial for making SMA-based technologies more reliable and longer lasting.
Right. I mean, if you're depending on a material to always return to a very specific shape, you definitely don't want it to, kind of get stuck in some slightly altered form.
Exactly. And that's precisely why researchers are exploring some really innovative designs, looking at new materials, different ways to either minimize this slip or even completely bypass it, especially for demanding applications, like you said, like in microrobotics or biomedical implants, where reliability is paramount.
Okay. So let's unpack this shape memory a bit more. We keep hearing about superelasticity and the shape memory effect. What's the science behind how these alloys actually remember? What's the fundamental mechanism at play?
It's fascinating. Both superelasticity and the shape memory effect, they're actually rooted in this solid state phase transformation that happens within the material's crystal structure.
Yeah.
You can almost think of it like water freezing into ice and then melting back again. But here it's happening within a solid metal. Superelasticity, which happens above a specific temperature, we call it the austenite finish temperature, or AFS. Well, this allows the SMA to recover large strains after it's deformed and then released. So just picture it. You bend a metal component, you let go, and it snaps right back to its original shape. No permanent bending.
Like it never happened. No lingering deformation at all.
Right. It's pretty remarkable. And this happens because when you apply stress, the material transforms from a phase called austenite to another phase called martensite. And this martensite phase, well, it's not stable at that temperature without the stress. So when you remove the stress, poof, it reverts back to austenite, and the original shape is restored. And often, the martensite at this stage exists as what we call twinned variants. Think of it like a deck of cards. You can shift the layers slightly, create different arrangements, but they're still the same cards, just oriented differently.
Different orientations of the same underlying structure.
Right.
Twinned variants. Got it.
Exactly. Now, the shape memory effect, it's related, but it typically involves a temperature change. So if you deform the SMA while it's in its lower temperature martensite phase, it'll hold that new shape. But then if you heat it up above its transformation temperature, bam, it snaps back to its original higher temperature austenite shape.
So, superelastic recovery is triggered by removing the stress at a higher temperature, and the shape memory effect is triggered by heating from a lower temperature deformed state.
Okay,
Got it.
precisely.
But here's the catch, and this is really important when we talk about this memory loss we mentioned earlier. If you push the stress too far, you can actually cause permanent deformation. This is what we call plastic deformation, and it's what you'd normally expect in a conventional metal. Like if you bend a paperclip too far, it stays bent. And in SMAs, this plastic deformation is really bad because it prevents them from fully recovering their shape. Even tiny imperfections in the material, like the boundaries between the crystal grains or different phases, can act as starting points for this unwanted atomic slip. And over time, as this slip accumulates, it gradually degrades the SMA's performance.
Okay, so this slip at the atomic level is the real villain here. How do scientists actually visualize and understand what's happening during this slip at such a small scale? How do they study it? Well, that's a great question. It really comes down to understanding how atoms move within the crystal structure of an SMA. You see, within this structure, there are specific slip systems, which are essentially pathways. They're combinations of planes and directions along which atoms can move past each other. And some of these slip systems are easier to activate than others, meaning they require less energy. So under stress, these easier pathways are more likely to be the ones where slip occurs.
So for atoms moving within the crystal, some paths are like taking the highway, while others are more like off-roading.
Yeah, that's a great analogy. For example, in the austenite phase of nickel titanium, or NITI, which is a very commonly used SMA, theoretical models predict that a specific slip system, known as the, let's see, 11100 slip system, well, this one has the lowest energy barrier. So it's the most likely pathway for slip to occur. And the exciting thing is that when scientists actually observe these materials under powerful microscopes, like electron microscopes, their observations often match up with these theoretical predictions. And this ease of slip is related to how much energy it takes to break and reform the bonds between atoms as they're shifting around during the slip process.
So it's all about the energy required for those atoms to move and rearrange themselves. How do researchers determine these energy requirements for different slip systems?
One really useful tool is something called a generalized stacking fault energy curve. We call them GSFE curves for short. These curves, they're like energy maps. They show us how the energy of the crystal structure changes as you slide one layer of atoms relative to the layer next to it. And the shape of these curves, they give us a lot of information. For instance, if a curve is asymmetrical, it might suggest that partial slip is more likely to occur. And in partial slip, the atoms don't move a full atomic distance. Instead, they create these planar defects within the crystal.
Planar defects, like disruptions in the regular stacking of those atomic layers.
Exactly, exactly. These defects, they can show up as something called antiphase boundaries or stacking faults. And it's interesting, research has shown that if you make the grains within the SMA really, really small, like down to the nanoscale, you can actually increase its resistance to this dislocation slip. There are techniques like equal channel angular extrusion, or ECAE, that can be used to achieve this grain refinement. And they've been really successful in alloys like knee-typite. It's basically squeezing the material through a die with specific angles to create this ultrafine grain structure. And this leads to a much higher yield strength, meaning the material can withstand higher stress before permanent deformation sets in.
So making the grains incredibly small actually makes it harder for the atoms to slip. It's kind of counterintuitive, isn't it?
It is, it is. And the reason for this is because these grain boundaries, they act as barriers to the movement of dislocations. Dislocations are these line defects in the crystal structure, and they're the main carriers of plastic deformation. So the more grain boundaries you have, the more obstacles these dislocations encounter, and the harder it is for slip to occur.
That makes sense. So it's like putting up more roadblocks within the material. Now we've been mainly focusing on the austenite phase. What about the martensite phase? Does slip happen there too? And are the mechanisms, are they different?
That's a great point. Yeah, absolutely. Slip can occur in the martensite phase as well. It's just that martensite has its own distinct crystal structure, so it'll have its own set of preferred slip systems. For instance, in 90HF alloys, where you have hafnium added, the martensite can take on either a monoclinic or an orthorhombic structure, depending on the amount of hafnium. And each of these structures has different slip systems that are energetically favored. For example, in the monoclinic structure, a likely slip system is 001-100, while the orthorhombic structure might favor 0101 to 100.
So the pathways for slip are kind of dictated by the specific arrangement of atoms in the martensite.
Exactly. And just like in austenite, some slip systems in martensite are more prone to something called dissociation reactions. That's when a full slip event splits into partial slips. And this, again, can lead to the formation of those planar defects, like the antiphase boundaries. And these tendencies, you can actually see them in the GSFE curves for martensite, where you see these local dips in the energy. We also see similar behavior in other SMAs like Cusinal, where slip on certain planes can create these antiphase boundaries. The dominant slip system often depends on how much energy it takes to create those boundaries.
So predicting exactly where and how the slip is going to occur under different conditions, it seems like an incredibly complex puzzle. How are researchers even able to model and predict this behavior?
Well, that's where computational modeling and simulations come in. They're really powerful tools. Techniques like density functional theory, or DFT, and molecular dynamics, or MD simulations, they allow us to model the energy landscape for slip and determine the critical resolved shear stress. That's the minimum stress needed to kick off slip on a specific slip system. And what's really valuable is that the predictions from these models often align really well with what we see in experiments, so giving us a deeper, more mechanistic understanding of how these things are happening at the atomic level.
So we're getting better and better at using computers to predict how materials are going to behave in the real world.
Absolutely. Absolutely. And these models, they can help us understand how different factors influence slip resistance. Things like the material structure, whether it's a single crystal or as multiple grains, the temperature, the specific chemical composition of the alloy, they all play a role. For example, research has shown that adding tantalum to Thiamine SMAs can make them much more resistant to slip in the martensite phase compared to adding zirconium. Researchers even use equations that consider things like dysregistry, which is basically a measure of how much the atomic lattices mismatch when they try to slide past each other. And this mismatch, this dysregistry, it creates resistance to slip. It's like trying to slide two pieces of sandpaper past each other. The rough surfaces create friction.
So it's like they're creating a virtual lab to test out all sorts of material recipes and conditions. Now, we've been talking about slip as if it's happening independently, but what about when that shape memory transformation, from austenite to martensite, when that actually occurs, can that process itself cause slip?
You're hitting on a really interesting point. The answer is yes. The very act of that phase transformation can actually induce slip in the austenite phase, particularly near the boundary between the two phases. Think about it. One crystal structure is transforming into another, and this involves changes in shape and volume. And these changes, they can create stresses and strain gradients in the surrounding material.
So it's not always a perfectly smooth transition. Can you elaborate on that? How does that work?
Well, imagine you have two materials that are trying to fit together, but they have slightly different shapes. That mismatch is going to create stress at the interface. And in SMAs, that stress can be enough to trigger slip in the austenite, even if you're not applying a large external force. What's more, this transformation-induced plasticity, it can actually train the material over repeated cycles of transformation. What I mean by that is the material might start to develop a kind of memory for a particular deformation path, making it more likely to deform in that way in the future.
So the transformation process can leave a lasting impact on the material's structure.
It is. And specific slip systems in austenite, particularly those with something called Berger's vectors, along certain crystallographic directions, like the 001 directions, they're more likely to be activated near that austenite-martensite interface. And this is because they're better at accommodating those strain gradients that arise during the transformation. Even the type of slip that dominates, like whether it involves something called W-type or T-type dislocations, which are specific types of defects that move through the crystal structure that can depend on the exact shape of the growing martensite plate and the orientation of the interface.
So the way that martensite grows within the austenite, that can also dictate how the austenite itself deforms.
Exactly. It's a very intricate dance between those evolving crystal structures.
So we've got all these different ways that slip can occur and potentially mess with the performance of SMAs. What are some of the strategies that researchers are exploring to actually prevent or at least minimize this slip and make these materials more reliable?
Well, one really promising approach is to introduce tiny nanoscale particles called precipitates within the main body of the SMA. These precipitates, they can act as obstacles to the movement of those dislocations, kind of like speed bumps for the atoms trying to slip past each other. And this helps to prevent that irreversible deformation, that permanent shape change, and promotes that clean, reversible thermoelastic transformation. This has been seen in alloys like iron, nickel, cobalt, or FeNiCo.
So we're adding even smaller obstacles within the material in addition to the grain boundaries. It's like a multi-level defense against slip.
Exactly. And these precipitates, they can be what we call coherent with the surrounding material, meaning their crystal structure matches up well with both the austenite and martensite phases. So during the transformation, they can actually be sheared by the changing lattice structure, which leads to elastic strain rather than permanent slip.
So they bend, but they don't break.
Right. And we can control the size and the density of these precipitates using carefully controlled heat treatments. We call it aging. We basically heat the material to a specific temperature for a certain amount of time to create these precipitates. And this can also affect the temperatures at which those martensitic transformations occur. And of course, grain refinement, like we talked about earlier with ECAE, that's another effective way to boost slip resistance by increasing the density of those grain boundaries within the material.
So it's about creating those internal obstacles at different scales, from those nanoscale precipitates to those microscopic grain boundaries. We've been talking about ways to tweak the material itself. But are there alternative ways to actually design SMA actuators that could help to overcome these limitations, especially in those tiny devices?
Yeah, absolutely. And applications like mesoscale and microscale robotics, researchers are exploring the use of low-profile torsional actuators. These are made from thin sheets of SMA, as opposed to those more traditional wires. And these designs, they can generate a surprising amount of torque for their size and weight. And another shift we're seeing is moving away from direct joule heating. That's where you pass electricity directly through the SMA to heat it up. We're seeing a move towards using external heating elements, often made from materials like nickel chromium or NiKR.
What's the benefit of using external heating?
External heating allows for faster response times and better energy efficiency because you can focus the heat right where you need it on the specific parts of the actuator that need to deform instead of heating up the whole device. And there are all sorts of designs being investigated, like Y-type actuators, Z-type actuators, and how you make them, especially the annealing steps, those are crucial for getting the best performance. These low-profile designs often include features like pre-drilled holes for easier mounting, and they might use bolting or riveting to make the electrical connections more reliable, which can be a lot tougher than soldering those really small scales.
So it's a matter of being smart about the design of the whole device, not just the material itself. Now, we've mostly been talking about shape memory alloys, but are there other materials out there that exhibit this shape memory behavior?
Yeah, actually, there's a whole broader category called shape memory materials, or SMMs. And this includes not just alloys, but also polymers, ceramics, and thin films. And each of these types of materials, it has its own unique set of properties. Its transition temperatures, how much strain it can recover, how much stress it can generate, how much it costs, and so on. But in general, SMAs, they tend to have the highest recoverable strain and highest recovery stress compared to those other types of SMMs. For instance, shape memory polymers. They can sometimes recover a lot of strain, but they don't generate as much stress as SMAs. Shape memory ceramics, they can handle really high temperatures, but they have much lower recoverable strain. And thin films, well, they're really useful in microelectromechanical systems or MEMS devices.
So it's a whole family of materials that can, kind of remember their shape, but they all have their own strengths and weaknesses. Bringing it back to SMAs, where are we actually seeing these materials being used today? And what are some of the big challenges that researchers are still trying to overcome?
Well, SMAs are being used in a really wide range of applications. In the automotive industry, they're used as actuators in things like rear view mirrors, climate control systems, and even engine temperature regulation. In aerospace, they're being investigated for use in morphing aircraft wings for better aerodynamic performance, and in those low shock release mechanisms for deploying spacecraft components. Robotics is another exciting area. SMAs are used as tiny actuators in microrobots and as artificial muscles in bio-inspired robots. And in the biomedical field, well, there are crucial components in things like stents for opening blocked arteries, orthodontic arch wires for straightening teeth, specialized surgical tools, and all sorts of implants.
It's amazing how diverse those applications are, but you mentioned some limitations earlier. What are some of the main hurdles that are still being worked on?
Yeah, there are still a few. Securely attaching SMA components, that can be a challenge. And in really tiny microrobots, the fact that SMAs have a low electrical resistance, that can make it hard to control them precisely. And getting them to consistently produce large strains and controlling their movement very precisely, those are active research areas. The energy efficiency of SMA actuators, that's another thing that researchers are always trying to improve. And of course, they're working on making them work over a wider range of temperatures, making them more stable over many cycles of use, making them respond faster, and making them generate more force or displacement.
So even though they have these unique abilities, there's definitely still room for improvement. Now, I'd like to focus on a specific area where SMAs are really making a difference: biomedical applications, particularly the use of nitty alloys. What is it about nitty that makes it such a good choice for use inside the body? And what are some of the concerns that come with using it in this way?
Well, NITI has become really popular for medical devices, and it's mainly because of its superelasticity and its biocompatibility. You see it used in things like those self-expanding stents that we talked about, which help to restore blood flow in arteries, and in orthodontic arch wires, which apply a gentle, continuous force to straighten teeth. And one of the great things about NITI for these applications is that you can really fine-tune the temperatures at which those martensitic transformations occur. That's crucial for making sure that the arch wire, for example, is applying the right amount of force at the temperatures found in the mouth.
That makes sense. You wouldn't want an arch wire to suddenly become stiffer or weaker just because someone took a sip of hot coffee. But I've also heard some concerns about the nickel content in these alloys. Is that something to worry about when they're being used in the body?
That's a very valid concern. While NITI is generally considered biocompatible, there are worries about it corroding in the mouth. The environment in there is pretty harsh, with changing pH levels, temperature fluctuations, bacteria, and all that mechanical stress from chewing and talking. And when nitty corrodes, it can release nickel ions, which can cause allergic reactions in some people.
So even though it's widely used, there's a potential risk of allergic reactions.
Yes. And because of this, a lot of research is focused on improving the corrosion resistance of nitty arch wires. Researchers are looking at different ways to modify the surface of the wires to protect them. Techniques like electrodeposition, plasma oxidation, and physical vapor deposition. These create a protective oxide layer that can really help prevent those nickel ions from being released. There's also a lot of research into how much friction these arch wires create when they rub against the brackets on the teeth, and how surface treatments and even natural lubricants like saliva can affect that friction. While the amount of nickel that's typically released from these devices is usually very low, much lower than what we get from our diet, minimizing that release is still really important, especially for people who are known to be sensitive to nickel. And to make things even more complex, researchers are using computer simulations, like finite element analysis, to try to predict how these nitty arch wires will behave mechanically under those complicated conditions in the mouth.
So it sounds like there's this constant balancing act between trying to take advantage of Nitty's amazing mechanical properties while also making sure it's safe to use in the body. And this has led to research into alternative materials, right? What's the latest on those nickel-free superelastic alloys for biomedical use?
Absolutely. The whole nickel allergy issue has really driven researchers to search for alternatives. And titanium niobium, or TNB alloys, have emerged as a really promising candidate. They can exhibit superelasticity, but generally their recoverable strain is not quite as high as nitty. And this is often because the changes in their crystal structure during transformation are smaller and they're more susceptible to slip at lower stresses. But the interesting thing is that by adding a third element, like zirconium, you can significantly increase that recoverable strain in these TiMB based alloys.
So it's about finding the right mix of elements to get those superelastic properties without any nickel involved.
Exactly. And scientists are using really sophisticated parameters, like something called elemental bond order, or Bow and d orbital energy level, or MBD, to predict the stability of different phases in these titanium alloys and how they're likely to deform. This helps them design new nickel-free alloys with better properties. And we're already seeing some great results with alloys like titanium niobium zirconium, TiNBZr, and titanium niobium tantalum, TiNBT, which have shown really good superelastic behavior. Another important factor, especially for bone implants, is how well these materials can dampen vibrations. The closer the damping characteristics of the implant are to those of the surrounding bone, the better the implant will integrate with the bone. And some studies have even shown that superelastic nitty can actually promote bone growth better than those conventional titanium alloys that don't have that superelasticity. This might be because it's better at distributing those mechanical stresses.
So the hunt for that perfect nickel-free superelastic alloy, it's a really exciting area of research. Now, we've talked a lot about how slip can lead to permanent deformation, but can the actual martensitic transformation itself contribute to that, that process of changing from austenite to martensite and back?
You're right, that's another important aspect. Research has shown that you can get plastic deformation, that permanent shape change, during both the forward transformation from austenite to martensite and the reverse transformation from martensite back to austenite.
Hmm.
And this happens when you apply stress during the transformation process. To study this, scientists have developed what they call a 3D unrecovered strain stress temperature diagram. It's basically a 3D map that shows how much permanent deformation you get under different combinations of stress and temperature.
A 3D map of permanent deformation. That's a really interesting way to visualize it. So what are some of the key takeaways from those diagrams?
Well, those diagrams show us that the amount of unrecoverable strain tends to increase exponentially as you increase both the stress and the temperature during those transformations. And what's even more interesting is that the reverse transformation, when martensite changes back to austenite upon heating, it can actually create as much or even more permanent strain than the initial forward transformation. There are some theoretical models that try to explain this. They're often based on the idea of strain compatibility, either at the boundary between the austenite and martensite phases or at defects like those grain boundaries we talked about.
So the shape change isn't always perfectly reversible, especially when there's a lot of stress or high temperatures involved.
Exactly. But those theoretical models, they don't always fully capture what happens at really high stresses and temperatures, because at those extremes, you start to get a lot of dislocation slip that happens independently of the transformation itself. And if you look at the material under a really powerful microscope, like a transmission electron microscope, you can actually see all those slip dislocations, which clearly contribute to that permanent deformation.
So it's almost like the transformation process itself can create the right conditions for that problematic slip to occur. Now, one last thing I want to touch on before we wrap up. I came across this really fascinating concept in our research. Superelastic metamaterials. It sounds like a totally new approach to achieving shape recovery. What can you tell us about them?
Oh yeah, this is a cutting-edge area of research, really exciting. Superelastic metamaterials, they kind of take this whole shape memory thing to a whole new level. Instead of relying on the material itself to remember its shape, they rely on a carefully designed structure at a very small scale. We call it a hierarchical microarchitecture. Imagine a lattice structure, but at a microscopic level. And the amazing thing is that these metamaterials, they can actually recover strains that are much, much larger than even the best shaped memory alloys like Niti, sometimes 4 to 6 times greater.
Wow, that's incredible. So the shape memory ability is coming mainly from the structure, not from a phase transformation in the material.
Exactly. It's a game changer because it means that we can potentially create materials with superelasticity using common, readily available materials. We don't have to rely on those specialized alloys and their phase transformations. And 3D printing or additive manufacturing is playing a huge role in making these complex structures a reality. It's opening up a whole new world of possibilities for designing materials with incredible properties. Who knows what kind of amazing applications we'll see in the future? It's like we're engineering elasticity itself.
It's really mind-blowing to think about. So, to recap, we've taken a pretty deep dive into the world of shape memory alloys. We've explored how slip happens at the atomic level, how that leads to performance problems, and the different ways scientists are trying to combat it through things like alloying and processing techniques. We talked about new designs for SMA actuators, the potential of nickel-free alloys for biomedical applications, the complex relationship between phase transformation and plasticity, and the exciting emergence of superelastic metamaterials. It's clear that understanding these fundamental concepts is crucial for advancing the design and application of SMAs across a wide range of technologies.
Absolutely. From the everyday gadgets we use to life-saving medical implants and cutting-edge robots, the future of these materials is incredibly bright.
And to leave you with a final thought, dear listener, given all these rapid advancements in material science, what incredible, previously unimaginable applications of shape memory and superelastic materials might we see in the years to come? Are we entering a new era where materials themselves have a kind of intelligence, able to respond and adapt to their environment in ways we're only just beginning to grasp? It's a pretty exciting question to ponder, and maybe it'll even inspire you to explore some of the latest research yourself. Thanks for joining us on this deep dive. We'll see you next time. All right, welcome.